There we go. So this thing's called a spirometer. And a spirometer measures breathing, how much air is flowing at one time. So when you look at a spirometer, you have to plug your nose, you put your mouth on a tube, and it's measuring the air going out of your lungs and into your lungs. You have to have your nose plugged, because otherwise when you think you're not letting air flow out of your nose, like you're just blowing through your mouth, you're not. You're blowing air out of your nose too. When you think you're just breathing through your mouth, you're not. You have a lot of flow through your mouth, but you're also letting flow go through your nose. So it has to be plugged, otherwise the measurements aren't right. Right, so you're going to blow into the tube, and you can see with the tube it goes down and up underneath that white cylinder over there. So see the white cylinder in the middle of the blue things? When you push air into there, it raises the cylinder, and it measures how much air is going into the cylinder. The stuff around the outside is filled with water. So when we get over there, be careful, because the blue things are full of water, and the little boxes on the table are full of electricity, and they don't like each other. So you have to be careful while you're working with them. So you're going to push air up and in. Every time you blow air in and out, it moves that little line at the very end called a spirogram. Oh, look at that. Pointer. Awesome. So over here on the very, it disappears. Crap. Nuts. Yeah. Cool and interesting, but lost the emphasis. But all the way over there on the left side of the picture, you can see that red line going up and down. It measures your air going in and out. Air in and out. It's a spirogram. And I said this in lecture, you absolutely positively have to know these 4 lung volumes and these 4 lung capacities that we're going out. The first one's a tidal volume. A tidal volume is a normal, relaxed breath. Let's say you're asleep. You're taking this nice, easy breathing. Breathe in, breathe out, breathe in, breathe out. I always imagine a tidal volume as I'm sitting on a beach watching the what come in and out. The tide go in and out. It's very relaxing. It's a relaxed breath. You use about 500 milliliters of air at a time, so about a half liter of air. The next one you need to know is what you can breathe in beyond tidal volume, and that's inspiratory reserve. So you take a breath, and you're about to breathe out, and then suddenly you want to breathe more in. That extra breath is your inspiratory reserve. The extra breath you breathe in is your inspiratory reserve. It's everything above tidal volume. It does not include the tidal volume. The next one is the expiratory reserve. It's the amount that you can blow out beyond tidal volume. So you take a breath, you relax your breathing. At the end of the relaxed breathing, you can still blow more out if you wanted to. This is a forced expiration. That expiratory reserve, when you're blowing out candles or you're blowing up a balloon, that's the extra stuff beyond a tidal volume you can get out of your lungs. I'm stressing what you can get out of your lungs because at the very end, after you've blown really, really hard, you're like trying to struggle to get anything else out. Do you still have air in your lungs? Yes, you do, and it's called your residual volume. So if you maximally exhaled everything you possibly can out, and then I plugged your nose and covered your mouth and measured how much air you have in your lungs, that's your residual volume. The only way to get that out is to pull a Mack truck up over your chest and smash it all out. So those are 4 volumes. When you look at this spirogram like this, those 4 volumes do not overlap on this chart. You should know how to draw the chart and what the different values are. Just like you had to know how to draw an EEG or ECG and know the different values. So the 4 volumes do not overlap. The 4 capacities all include 2 or more volumes. So if I take my tidal volume and I add my extra inspiratory reserve, that's my inspiratory capacity. A normal breath in, plus that extra stuff I can breathe in to like go underwater. That's inspiratory capacity. So the way you calculate that is IRV plus TV is inspiratory capacity. The next one, that's, by the way, the top half of the chart. If you blocked up that chart into 4 sections, the inspiratory capacity is the 2 top sections. The 2 bottom sections are called the functional residual capacity. This is what resides in your lungs after you relaxed exhale. Can you still blow air out? Yes, you can. Yep. So you can still blow the ERV out. You still have the RV that's hanging out there. So the FRC is the bottom half of the chart. It's the expiratory reserve volume plus the residual volume. So if I subdivided that chart into just two halves, the top half is the inspiratory capacity and the bottom half is the functional residual capacity. The last two, if I looked at the 3 volumes of air that I can move, the 3 that I can get rid of, what's the only one I can't get rid of? The one that makes it so that they don't collapse, which is called the residual volume, right? So if I look at the other 3, the inspiratory reserve, the tidal volume, and the expiratory reserve, those 3 together are my vital capacity. Vital means life. So it's talking about the 3 that you can move to stay alive. Can you move the residual to stay alive? Nope. The only benefit to life it has is it keeps your lungs from collapsing. So the vital capacity are the top 3.
That's pretty beneficial.
Huh? It does. I said the only benefit to life is that it keeps your lungs from collapsing. The 3 that you can, but you can't move it. The 3 that you can move to stay alive are the top 3. And then the total lung capacity is you add all 4 volumes. You take the deepest breath you possibly can. I plug your nose, I plug your mouth, and I take an x-ray of your chest. I can measure that volume and say, hey, this is your total lung capacity. This is all of the air that you can hold at one time. So it's all 4 volumes added together. And we're going to play with that spirometer over there, and we're going to look at and measure these different values. So the TV, remember, is your normal breath. The IRV is what you can breathe in beyond a normal breath. If I add those 2 together, what is it? It's got to be a capacity because I'm adding them, right? It's the inspiratory capacity, the amount I can breathe in. I take a breath and I relax. At the end of that relaxation, all the air that's left in my lungs is called the functional residual capacity. It's made up of 2 things that haven't left my lungs. What are they? ERV and residual. Yep. The vital capacity are what? The 3 that I can move to stay alive. The only one that's not included in the vital capacity is the what? The RV. And the total lung capacity is what? Yep, all 4 added together. So all 4 volumes added together. The other school I teach at, we do this old school. We don't use that fancy thing that hooks up to a computer. They actually blow into a tube 3 times and measure the volumes. So they blow into a tube for a resting. What are they blowing in first? A resting breath. Tidal volume. So they calculate the tidal volume. The next thing they do is they take a deep, deep, deep breath, everything they can, and they blow everything they can into this little tube. What did they just blow into the tube? They took the deepest breath they could and they blew everything they possibly could move out of their lungs. They blew out their IRV, they blew out their tidal volume, and they blew out their ERV. What did they just blow out altogether? Their vital capacity. The only thing left in their lungs is the residual volume at that point. So now we know their tidal volume, their vital capacity. The next thing I have them do is I say, relax your breath. Just relax. And they go, ha. They put the tube up and they blow what they can out. What's that little volume called? The ERV. The residual, or the expiratory reserve volume is the only thing left they can blow out at the end of a normal breath. By those 3 values, I tell them, your residual volume, since we can't measure that, is 1200. Calculate everything else, and they can do it. So because they know those 3 values, and I give them residual volume, they can calculate their TLC because they added all 4 things together, right? They can calculate their IRV by taking the tidal volume and the ERV and subtracting those 2 things from the vital capacity. If you look, the vital capacity is IRV, TV, and ERV. All you have to do is subtract the TV, the ERV, and you've got the IRV left. So it's kind of interesting how we have to do these old school sometimes. But these values are really important because they tell you, are you able to get a full breath in? Are you able to get a full breath out? Are you able to move lungs at what speed? Which is the next point. So we're going to hook you up to the little spirometer, and we're going to say, when I say go, you blow out as fast as you can. And we go click, and you're blowing. It's measuring how fast you can move that air in your lungs. People that have really sucky elastic tissue, what's going to happen to their ability to move air out of their lungs? Faster or slower? Way slower. So when you're blowing out slower, if it's under 80, we go, uh-oh, you've got an elastic problem or an airflow problem. Think about asthma. With asthma, the airway shrinks down. If you shrink the airway, what would you do to the radius? Made it smaller. What did you do to the resistance? You made it higher. What did you do to their flow? You decreased the flow. Are they going to be able to blow out their air in their lungs as fast? No. So the two diseases in general I just told you were asthma and emphysema. Asthma with the airway, emphysema with the elasticity. So if somebody has a respiratory disorder, you're going to see a decreased forced expiratory volume. The FEV1 is how much they can blow out in 1 second, and it should be over 80%. So it's telling you what their maximum airflow rate is. And FEV2 was what? How much they can blow out in 2 seconds. So over those first 2 seconds, they should get at least 90% out. At least. And then FEV3 would be within 3 seconds. Within 3 seconds, you should have at least 97% out. If they fall below those numbers, then we say, uh-oh, you've got a respiratory problem. And we diagnose them from there. So now you know what FEV is, and you know what the different values on a spirometer are. So if I asked you a question like this one, after a normal expiration, the volume of air in the lungs is called what? After a normal, relaxed expiration, what's left in the lungs? So what can you say about number 1? True or false? False. What about number 2? Is the functional residual capacity still in the lungs after a normal breath? Wow, nobody wants to talk about it, huh? How about number 3? Is the residual volume still in there? It is. That's true. That is in there. How about expiratory reserve? After a normal breath, is there expiratory reserve still in your lungs?
Oh, yeah.
Yes. So, whoa, now we have a problem. We know that at least 2 of these are actually still in the lungs. What's the right answer? Why is it number 2? Because FRC is both residual volume and expiratory reserve. FRC is what's left in your lungs after a normal exhalation. After a maximal exhalation, what's left in your lungs? The residual volume, the leftover stuff. That maximal expiring, that extra breathing out, that's the expiratory reserve. So you need to know what these different values are on a chart. Like respiratory dysfunctions, there are 2 general types. You want to remember with obstruction, it doesn't mean that they have like a carrot lodged in there or they have a big tumor in there or something. Obstructive means that they can't get air out. And the reason I'm stressing this is because with something like asthma, it's the airway, but there's nothing stuck in their airway. Their airway has shrunken down, and what happened to their flow? The flow decreased. What are you better at doing? What are you using energy to do? Breathe in or breathe out? Breathe in. You're good at breathing in. You have muscles that are developed over all the years of your life. These muscles are developed. They're strong muscles. So if you need to do some kind of forced breathing, what are you going to be better at? Breathing in. So when somebody with asthma shrinks down their airway, what do they have to do? They use power to move it. Which muscles are going to be the best? The diaphragm and the external intercostals, right? So they can breathe in powerfully, but what can't they do? They can't get it out, right? So if somebody has asthma and you close your eyes and listen, what do you hear? By the way, if somebody's having an asthma attack, don't just close your eyes and listen. That's rude. Yeah. They're going, you're hearing the inhalation part, but what are they not getting out? They're not getting the carbon dioxide out. How's it going to make them feel? More panicky. What are they going to try and do more? Breathe harder more, which makes them anxious, burning more metabolism, makes them build more CO2 up. So they're constantly building CO2, getting more and more anxious feeling, and then eventually they pass out, right? So with asthma, they can't get the bad air out. With emphysema, it's the size of their alveoli that changes. It's not the airway, but it's still an obstructive lung disease. Because what have they lost? They've been smoking all these years, and what happens? The elasticity. Their lungs aren't elastic, which means they can't do what now? They can't collapse properly. So they can't get the air out. When you watch them, they actually have kind of developed muscles in between their ribs and their abs, because what are they always doing to breathe? They're always forcefully exhaling. They're always going... They're having a problem getting the air out. They have to forcefully exhale to get it out. They get plenty of air in. In fact, when you look at their chest, how do we refer to their chest when they have emphysema? Barrel chest. They have a big chest. So their lung capacity is huge. The problem is they can't get out what volume of air? What's the volume of air they can't get out? The same volume of air you can't get out. What volume of air can you not get out? Residual volume. What's the difference between yours and theirs, though? Theirs is way bigger. Yep. They're way bigger because they've lost the elastic properties and they can't collapse the alveoli. So that dead space gets bigger and bigger and bigger. All right. Bronchitis would be another example of obstructive lung disease. So much mucus in the airway they can't get the air out properly. By the way, bronchitis plus emphysema is what? Anybody know what it's called? COPD, yeah? Chronic obstructive pulmonary disorder or disease. By the way, it says it right in the name, what do they fall under? Chronic obstructive pulmonary disorders. Obstructive, yep. And then restrictive means that they can't get air in. It means that their lungs have been restricted to a specific size, a small size. It's like they're wearing an iron jacket or an iron vest that doesn't expand. They can only breathe until they hit the walls of the iron vest and they can't breathe more in. So their volume, when you look at volume changes, their total lung capacity dramatically goes down. Their residual volume stays about the same. Their tidal volume stays about the same. But their total lung capacity drops, which means that their inspiratory reserve and their expiratory reserve have to change. When you look at somebody with asthma or emphysema, they can't get the air out, so what value goes up? Can't get the air out. The residual. The residual volume goes up. Their total lung capacity stays the same, which restricts the other values. Like, look at their ERV. It's tiny. So think about it this way. You've got a big ERV. When you cough, you get a powerful cough. When they cough, what's going to happen? They have to suck you to cough, right? Which is bad because they already have really poor lungs. What are you worried about getting in there that you're trying to cough out? Things like bacteria and debris. Okay, so you need to know how to put together a spirogram. You need to know the different values, whether it's volume or a capacity, the values. Not the number value, I'm sorry, but the actual names of the values. And then you need to know what the two major groups of diseases are in a subcategory. And then last, you need to know how to calculate their airflow. So pulmonary ventilation is the amount of air you move in and out of your lungs in 1 minute. When we said moving a certain volume out of your heart in 1 minute, what was that called? 1 minute. Stroke volume is 1 beat, right? Cardiac output is a minute. Pulmonary ventilation is the equivalent of cardiac output, except that we're talking about air. Cardiac output was heart rate times stroke volume, which is how much you push out in 1 beat. This is respiratory rate times what volume for 1 breath? What's your 1 normal breath? Tidal volume. Pulmonary ventilation, you take your tidal volume, which for this person is 500, times their breathing rate, which is 12 breaths per minute, and it comes out to 6,000 milliliters every minute. It's 3 2-liter bottles of air you move in a minute. The problem is that air is talking about everything that goes beyond your nose. What do you already know from lecture about the space between your nose and your actual alveoli? It's dead space. It's worthless. You bring the air in, but it never gets exchanged. So you bring all this good air in, and it basically sits stale there for a second, and then you blow it right back out. You didn't get to use it. It's called pulmonary ventilation.
Pulmonary ventilation is the
Pulmonary ventilation is how much you move beyond your nose in a minute. Think of it that way. The anatomical dead space is that dead air that's in between your nostril and the alveoli. You cannot get exchanged in the anatomical dead space. Your anatomical dead space is about 150 milliliters for the average person. So you've got about a foot of tubing there that takes up 150 milliliters. So to do a true calculation of what's getting into your lungs, you actually have to get rid of the anatomical dead space. So we can take their tidal volume, subtract the anatomical dead space from it, and then multiply it by respiratory rate. So a real accurate measurement of what's getting into your lungs is actually 500 tidal volume minus 150 for the anatomical dead space and then multiply that by the respiratory rate, which is 12. So a more realistic one would be about 4,200 milliliters of air. So instead of 3 2-liters of air, you have 2 2-liter bottles of air. You've gone down by about 30%.
You know how certain populations are made to be survival of the fittest? And certain populations were raised in the desert for a while, certain populations were raised in like Alaska for a while, and Canada, like polar regions. So is that why certain ethnic groups have bigger noses than others because they need a bigger space to warm up air?
I couldn't even answer that. I've never even heard of that theory.
I'm just thinking, like that. Maybe that's why certain cultures have bigger noses, like Irish people. Maybe that's why, because they need more space.
Are you picking on Irish people?
No, I'm Irish. I'm Irish. So I'm wondering if because my ancestors, wherever they were at the time, they needed more room to warm up the air that they're breathing in before it hits their body because it's too cold.
Well, I'm just thinking of people that I know with big noses, and I have a couple of African American friends that actually have kind of large noses, which totally blows that theory out of the water.
Theirs is wider, so it's shorter, so they need less.
But the nostrils are still bigger, right?
Yeah, but they're wider and shorter, so they need less space to cool off air.
Shorter? Okay, I'm not thinking their nose was any shorter than mine.
Okay, like the majority, though.
Okay, well, I'll let you Google that and look it up, because I can't.
I wonder if that would be why. Because that's about cooling or warming off air.
It makes sense, but I can't. You'd have to go and look up online somebody that's done that study. Get back to us on that. Now you have a homework assignment. See what happened? You just assigned yourself some homework.
I just did.
All right.
Okay.
And then alveolar dead space. So the anatomical dead space is from the tip of your nose all the way down to the alveoli. The alveolar dead space is actually the space inside the alveoli. So when you breathe the air in, the only way to get exchange is to make the air touch what? That wall, right? If the air doesn't touch the wall, there's no exchange. The air can come down in, it can circulate around in there, but if it never touches the wall, it can't move over and diffuse into the capillaries. So that air you bring down in the center of the alveoli gets pushed back out too. So a lot of the air that comes into your lungs is actually wasted too. A lot of waste going on there. It is. It's like I said, you just need... I think we should just have, like, some plastic surgeon put noses where our nipples were and just breathe directly in, right? I guess that's more useful if you're a male, but... What? Why they say not to? Yes. Yeah, you're not supposed to breathe through your mouth, even when you're running. You're supposed to breathe in through your nose and exhale through your mouth. Because when you breathe in through your nose, you have all that airway that's full of blood vessels that warms the air. Yeah. Okay. So we already calculated alveolar ventilation, talked about alveolar dead space, and then the garden hose story. And this is so, to me it's funny because my very first semester teaching, I had this student, we're halfway through the semester talking about respiration, right? And nobody has really talked up my first semester. And then suddenly I tell this story and this girl just blurted out. And so I was saying when I was in grad school, one of my professors told us about a story he had heard. This kid, he's at a party, he's hitting on some other guy's girlfriend, and then the other guy didn't like it. So they go running down the street, and the first kid kind of gets away from the other guy and jumps over this fence and looks around and sees a garden hose and a swimming pool and says, I'm going to hide. This is brilliant. He takes the garden hose and slings it out to get all the water out, grabs a garden gnome, puts it in his pants, and falls backwards in the pool. So he sinks to the bottom of the pool because of the garden gnome, right? And he's breathing through the tube, and he suffocates to death. Why? Nope.
Because it takes too long to get down the tube.
Because what did he just do to his anatomical dead space? Yours is about a foot to a foot and a half long. What did he just do? He made it 25 feet longer if it's a 25-foot garden hose. So that air, that anatomical dead space, there's no exchange going down that garden hose. There's no exchange going in his anatomical dead space. He would have to get fresh air from all the way at the other end of that tube, down into his lungs and exchange across, then blow it all the way back out. Not realistic. That's too much. Yep. Because he had a garden gnome in his pants and couldn't get out of it. You'd think so, but when you're panicking and underwater, maybe you don't think that quick. You must be a swimmer then. Yeah. So yeah, garden gnomes are made out of cement. And it pulled him down. So I had this student that goes, "That's not true." And I went, "Oh crap." And I said, "Why?" And she said, because I snorkel all the time, and I put a tube on my mouth, and I can breathe. And I said, wow, how long is your snorkel? And
25 feet.
yeah, and you know, when you go under with a snorkel, you do intentionally breathe a little more forcefully to get the air out, and that's why, because you just doubled your anatomical dead space. So I went to find the story, and I went looking on Google all over the place and couldn't find it, but I did find a cool one about a guy that did the same thing. He dropped his keys over his boat while they were out drinking, and so he goes, oh, I'm going to get my keys. And he goes back, gets a garden hose, and gets a cinder block, and does the same thing. He tied the cinder block to his waist, jumped over the boat with the hose hanging off the edge of the boat, and he went down, and he's like, Luckily his buddy went down and cut him free, and he came up. So that you don't float up, and so that you're forced to be down there and walk on the bottom. So that you're forced to walk across the bottom.
So the guy in the pool, that's to prevent the other guy from eating.
So he went all the way to the bottom of the pool. Yep.
That's such a good idea.
Until you die, it's a great idea. Yep. So anyway, and then I had another student when I told that story that's like, well, what about those old, like, scuba diving things? They're not scuba, but the old dive suits with a big metal bowl, fish bowl on their head, you know what I'm talking about? And they had a tube running to the surface. Well, what about them? If you follow the tube up on the surface of the boat, what's there sitting there? There's actually a pump pushing the air down. So the good fresh air is coming down the tube, and the bad stuff's going out underneath the fish bowl. So that's how it works. They do?
Yeah.
Isn't it with... That's right, and Robert De Niro, isn't it?
Yeah.
Okay, so if I ask you this question, you need to be able to answer this question for things like quizzes and tests. If a patient has a tidal volume of 300 milliliters and a dead space of 100 milliliters with a respiration rate of 20 breaths per minute, what is their pulmonary ventilation? All right, how many people think it's number 1? How many people think it's number 2? How many people think it's number 3? How many people think it's number 4? So it looks like most people think it's number 2, right? Those people are wrong. Number 2 is incorrect. Anybody want to tell me why it's incorrect? What is pulmonary ventilation? It's respiratory rate times the tidal volume. 6,000 is the correct answer. So 300 times 20 is 6,000. When you get beyond this class and you take placement tests like MCATs, NCLEX, any kind of those placement tests, are they going to give you more information than you need? Count on it. Almost every question will have more information than you need. Almost. So if you know what you're talking about, you'll never get fooled. That pulmonary ventilation, if you knew what pulmonary ventilation was, you knew it was respiratory rate times tidal volume. What was everybody calculating? Alveolar ventilation, right? Which is tidal volume minus the dead space, then times the respiration. This is not alveolar. If it asks for alveolar on a test, use all 3 pieces. If it asks for pulmonary, just use 2. Next concept. So this concept is not on the quiz next week. This concept is possibly on the test, though. So local controls that act on smooth muscle airways and arterioles that match blood flow. This is going to that perfusion versus ventilation stuff. And I stressed this in a lecture today, and I'm stressing it again. I want you to underline the word bronchiolar, and I want you to underline the word arteriolar. What's the difference between those 2 things? One carries air. Which one carries air? Bronchiolar. What's the arteriolar carry then? Blood. What is the primary determinant of the airflow? Carbon dioxide. What's the primary controller of the blood flow through the lungs? Oxygen. The determiner of perfusion or blood flow through the lungs is oxygen. The determiner of airflow, getting air from outside in, is carbon dioxide. They're 2 totally different structures. So if I have carbon dioxide building up in my lungs, what happens to my airway? My airway will it decrease or increase? So will it constrict or will it dilate? If I have a lot of CO2, common sense tells you, do I want to keep it or get rid of it? What do I do to get rid of it? Open the tube or close the tube? Open it. So when you have a raise in carbon dioxide, you need to open the airways. The bronchioles will open up and you will be able to get rid of air. Just the opposite down here is oxygen. If oxygen levels in the blood get really low, guess what they do with the lungs? They constrict. This is why this is tricky. Every other blood vessel in the body, every other tissue in the body, when you have low oxygen, what's that blood vessel do? It dilates. If you have a muscle that needs oxygen, it's low in oxygen, what's it do? It dilates its arterioles to increase the blood flow so you get more oxygen to it. The reason this is different is because the significance of this. If I have really low oxygen in my lungs, is it going to be easier to pick up oxygen or more difficult? If I have low oxygen in my lungs, is it going to be easier to get it into my blood or more difficult? More difficult. Don't even think about the constriction. It's more difficult because you already know the concentration differences, right? If it's low in the blood and now it's low in the lungs, what's going to happen to the rate of diffusion? It slows. Remember, a smaller concentration difference slows down the rate of diffusion. We have normal high oxygen and it goes right into the blood, right? Now it's down lower. What do you want to happen here? Do you want the blood flow going faster through the lungs or slower? You want it going slower. You want it going slower through the lungs so you have more time for the oxygen to do what? Diffuse into the blood. And I think I used this analogy in lecture today, but think of it. If you're an oxygen molecule and you're standing on the hemoglobin freeway, do you want those hemoglobin molecules flying by 80 miles an hour? No. If you're a lonely oxygen sitting along here, you want those hemoglobins going by really slow. What do you have to do to the blood vessels to make them go slowly? Constrict them. You squeeze the blood vessel down, the blood flows slowly, and then you have a chance to jump on the hemoglobin. This is a tricky one because every other tissue of the body, if you have low oxygen, you open up the blood vessels, not here. Here, if you have low oxygen in the lungs, the blood vessels start squeezing down to slow the flow to pick up more oxygen. It gives you a chance to saturate that hemoglobin that we talked about in the lecture today, to get more oxygen on the hemoglobin. So it's an important concept. And here's how it's illustrated. So what's the question say? It says, area in which blood flow is greater than airflow. So you have very little airflow. What's going to happen to your CO2 levels? Your CO2 is going to increase because you're not exchanging very well, right? What's going to happen to the blood vessels? Blood vessels. What's going to happen to the structure because of CO2? CO2 is going to dilate your airway, right? It's going to try and get rid of the bad CO2. What is going to happen to your oxygen level if you have low airflow? It goes down. What happens to the blood vessels? You have low blood flow, the blood vessels constrict. Yep. So you can see that pathway here. And then the next slide is just the opposite of it. So it just says if there's more flow going into that area, you do exactly the reverse. So if I ask you a question like this, if CO2 levels are high and oxygen levels are low, what happens when the CO2 levels are high? Something dilates. So what's going to dilate? The bronchioles. So we can narrow this down. It's got to be number 1 or number 2, right? Because it says 3 and 4 are constrict. The second part of the question is oxygen levels are low. What happens? The arterioles constrict. So it's number 2. Bronchioles dilate, arterioles constrict. All right. And then gas exchange of oxygen and CO2, talk about this a little bit. The whole purpose is that you're trying to get the good stuff in and the bad stuff out, right? It's the whole purpose. Where do you get diffusion or exchange? Where do you get exchange in general? Always at capillaries. Everything exchanges to the capillaries. Where do you get oxygen exchange? Capillaries going into the lung and capillaries going into all the other organs, right? So the pulmonary capillaries are going to exchange with the alveoli because they're only 1 cell thick. And then the systemic capillaries are going to exchange with the tissues. They'll push things into the extracellular fluid in between the cells, which is called interstitial. And then the interstitial fluid will put it in the cells. So there's your gas exchange. When you breathe in, quote-unquote, fresh air, The air outside is about 79% nitrogen, which is worthless to you. The only way it's made useless is if trees take it in, and then you eat the trees, or plants take it in, you eat the plants. So that's how that nitrogen is useless. Otherwise, you just breathe it in, you breathe it right back out. Oxygen is about 21% of the atmosphere. So a little over 20, close to 21. The oxygen is the important thing, but when you breathe in air, number one is you dilute it with water. So you're reducing the oxygen concentration because you're adding water in there, so it reduces your oxygen. So now you're automatically below 21% oxygen. Then, as you bring it down, you have to bring it through all that dead space and all that stale, nasty air. So as you're breathing the stale, nasty air out, it gets stuck in the dead space, and you breathe fresh stuff in that mixes with the dead space air, and you pull it down into your lungs. How you want to visualize this is if I have 2 glasses of water, like this. This one's dirty water, and this one's clean water. And I have to get this water over to here. Or you can say this air and this air. Clean air, dirty air. And I try and do this and swap them. What's going to happen? Am I going to get this clean water into this glass?
No.
I'm going to get some of it into the glass, but is it all going to be perfect? No, it's going to mix with the dirty stuff as I cross the 2 tubes, the 2 glasses. So every time you breathe in, you're mixing with stale, old air. So the 2 reasons that your air is not exactly the same as the atmosphere is because you're saturating with water in the nasal nares in the airway. And the second thing is that you're mixing with dead air space. I hope that wasn't toxic because I just rubbed my nose. Now I'm going to die. Great. Right. Yeah, if I start wheezing, you close your eyes and tell me what's happening. Okay, so by the end of inspiration, you actually only have about 15% oxygen in your air. The good thing is you only need 5% to stay alive if you're relaxed and breathing. So you can hold your breath, and then that goes from 15% down to the 10% because of normal breath, and then it goes to 9, 8, 7, 6, and then when it gets down around 5, then you've got to breathe again. You have to breathe again. Yeah, so why would you panic? Because you don't have enough oxygen? Because you have too much CO2. Yeah, because you weren't letting the CO2 out. All right, numbers to be familiar with. In your lungs, in the atmosphere, there's about 160 parts oxygen out there. The pressure of oxygen is about 160 millimeters of mercury. But by the time it gets down into your lungs, it's only 100 millimeters of mercury because you've diluted it. It's dirty now. So in your lung, it's 100. To be able to get this oxygen from your lung into your blood, what do you know the concentration of blood oxygen has to be, or the pressure of blood oxygen has to be? Higher than 100, the same as 100, or lower than 100? It has to be lower than 100. Because of diffusion, it goes from the lung down into the blood, and then you can carry it away. So you automatically know the alveoli has to have a higher oxygen concentration to be able to get it down into the blood. Right? And then we talked about this already. So a small portion of the total alveolar air is exchanged with each breath, keeping it at 100, so it stays consistently at 100 in the lungs. But then as you bring that old, stale, dirty blood up to the lungs, it's low in oxygen, so the oxygen races to where it's low concentration, right? And then here's the picture. You can see. I have no mouse to move, but you can see up in the lung, up in the top, it has 100 parts. Down when you're looking at the arteriole side, what color is the arteriole side in this picture by the lungs? It's blue. Remember, arteries in the right side of the heart carry away from the heart, the oxygenated blood, go to arterioles that go into the lungs. So over there on the left side, the blue side, you can see that the oxygen is only 40 parts. If it's 100 parts in the lungs and 40 parts in the blood, where does it go? It goes down into the blood. It goes from high to low concentration. And then it goes all the way into the venules and then the veins, the pink side, into the heart. Is there any exchange along there? None. And then it goes down into the venules and then the veins. Any exchange? Nope. And then it goes to the systemic tissues. So you can think of muscles or liver or stomach or whatever you want. Those cells are always metabolizing, so they're always low in oxygen. Always. So where does the oxygen go? From the tissue to the blood or the blood to the tissue? Blood to the tissue. It's 100 parts in the blood, it's only 40 parts in the tissue. It's going to pull it out of that high concentration blood and pull it down into the tissue until it hits what? Equilibrium. And at the point where it hits equilibrium, it's going to be at 40. That blood's going to move out of the tissues at 40 parts of oxygen into the venules, the veins, back into the heart. Goes into the arteries, arterioles, and then back into the pulmonary circulation again. It's that pathway all the way through. And exactly the same thing happens when you're looking at CO2. CO2 in the lungs is only 40. If you want to put CO2 into the lungs compared to the blood, what value does the blood have to have? Higher than 40, the same as 40, or lower than 40? If I want it to go from the blood to the lungs, the blood has to be what compared to the lungs? Higher. So if you look at this picture, it's about 46 down there. So over in the blue section, when you're looking at that arterial over in the lungs, the CO2 is about 46 parts, right? The parts of pressure. In the lungs, it's only 40, so where does it naturally want to go? Lung to blood or blood to lung? Blood to the lung. So it goes blood to the lung. And then, if you look at the atmosphere has 0.03, less than a tenth. It's actually 0.03% of all the air out around you is carbon dioxide. Not very high. So you've got 40 parts of carbon dioxide in your lungs, like practically zero outside. Where does it want to go? It wants to fly outside. Yeah, it wants to move it right outside. It's this process of exchange. You take that low carbon dioxide blood now at the lungs, you push it all the way down to the tissues, which are high in carbon dioxide because they're living and metabolizing. That high carbon dioxide goes into the blood, and then you carry it to the lungs and you exchange it again. So what do you know about the carbon dioxide in the tissue compared to the blood? We're talking about muscles, livers, other organs besides the lungs. What do you know about that tissue compared to the blood with CO2? The CO2 has to be what in the tissue? Higher. That way the CO2 goes from the tissue to where? The blood. And we take it to the lungs. And the lungs are lower than the blood, so it goes out to the lungs. And then the atmosphere is lower than the lungs, so it goes outward again. So if I ask you a question like this, the oxygen moves by diffusion into the metabolically active tissues because... So oxygen moves by diffusion into the metabolically active tissues because... How about number one? Because the oxygen content's the same as the blood? What's that called? They're both the same. They are both at equilibrium. Yep. You know that's not right. Because at equilibrium, does the stuff move? No, there's no net exchange. So you cross that one out. If it goes from the active tissue into the blood, it's because the oxygen content is what? So it moves from... Oh, by diffusion into the metabolically active. I was like, that doesn't seem right. Because the blood is higher than the tissues. So oxygen content is lower in the tissue than the blood, number two. If the oxygen content were higher in the tissue than the blood, where does it go? Into the blood, right? So it can't be number one. It has to be number two. It can't be number three either because that's equilibrium. Right, and then the last slide here. The other factors affecting the rate of gas transfer. These are Fick's laws again. So Fick said that if you increase the surface area, what do you do to the rate of diffusion? You speed it up. More surface area, better diffusion. In emphysema, they have normal sized lungs, but the problem is they burst the walls of the alveoli. So what happened? What did they do to the surface area of their lungs? It decreased it. What did they just do to the rate of diffusion? Slowed it down. The diffusion of what? Oxygen or carbon dioxide? Both. So where are they not getting in efficiently? Oxygen. Where are they not getting out efficiently? Carbon dioxide. If CO2 is staying in their body longer, what else is hanging out with it? Acids. Yep, so people with chronic emphysema, other than having the breathing problem, what else do you know about their blood all the time? It's too acidic. Their blood's so acidic, and we'll talk about this in acids and bases later. When your blood's acidic, proteins don't work right. Your neurons don't work right. Your neurons start shutting down. So what symptom, what physical outward symptom would you see other than breathing issues in people that have emphysema? They're always tired. Have you noticed that? If you see them, they don't want to get up and move. My former father-in-law had emphysema. The guy was always in the chair. I mean, great guy. When he needed to go, he'd take his oxygen tank. But man, he was miserable if he had to move from the chair. He wasn't a big guy either. I mean, he just had no energy. What's interesting, and we talked about this the other day, normal breathing takes about 3% of all of your energy. When you exercise, it takes about 5% of all your energy that goes into breathing. When you have a disease that affects the lungs, it puts your energy requirements up to 30%. So he wasn't fat. He was a pretty skinny guy, He's burning calories like you wouldn't believe, because what was he doing? He was constantly working to breathe. Yeah, constantly working his muscles to breathe. All right, so think about the surface area. The next is a thickness. So if I start putting scar tissue, or I start putting mucus along that membrane, what happens to the thickness overall that I have to diffuse across? It gets thicker. What happens to the rate of diffusion? It slows down as a result. Yep. So it slows down as a result. All right, and then here's where we picked up in lecture. All right, so I'm going to stop this recording and get it converting so we can post it online.